So dear students, I welcome you for the today's lecture where today we are going to discuss the resistances, the different resistances in a slab, cylinder and the sphere. Resistances because of the conduction and resistances because of the convection that we are going to discuss today. So basically, you require the steady state heat conduction in the plane wall, that equation, basic general heat conduction equation that is required, and the Fourier law that is required. So let us see at the figure. The temperature is maintained on one side, that is 20 degrees Celsius, and at the another end that is maintained at 3 degrees Celsius. However, the intermittent temperature that is calculated as 11 degrees Celsius. So that is the one dimensional heat conduction in the x direction that is assumed. So it is the heat transfer through the wall of the house that can be modeled as one dimensional steady state heat conduction. Then the rate of heat transfer into the wall minus rate of heat transfer out of the wall, which is equal to the rate of change of energy of the wall. Because in this basic general equation of energy balance or material, any balance equation, that is input minus output, which is equal to generation minus consumption. So is there any generation? No, no generation is there. And here the generation or consumption and the rate of change of energy term, that is also there. So this is the rate of change of energy term. Here we are assuming the steady state operation. As it is a steady state operation, so change in the internal energy because of the changes in the temperature, that is considered to be the zero. That is dt upon dt, that is taken as zero. This is talked in terms of the dE energy, internal energy, or you can also write in terms of the dt, change in temperature with respect to time. This Fourier law of heat conduction, that is Q, which is equal to minus Ka dt upon dx. So after integrating it from distance x is equal to 0 to L, the same figure, T1 is the one side temperature, T2 is the second side temperature, where temperature T1 is higher and temperature T2 is less. So from higher temperature T1 to the temperature T2, the heat will be transferring. That is why is in the x direction. Uh, Considering this small strip dx, and that is why we can integrate it from x is equal to 0 to L. The Q conduction for the wall into the dx, which is equal to minus Ka dt from temperature T to the T1 to the T2. Then Q dot, which is the in watts, that is Ka into T1 minus T2 upon L. So after integration you will get Ka T1 minus T2 upon L. So the rate of heat conduction through the plane wall is proportional to the average thermal conductivity, the wall area and the temperature difference, but is inversely proportional to the wall thickness L. Once the rate of heat conduction is available, the temperature Tx at any location x can be determined by replacing the T2 by T and L by the x. That can be also calculated. Now coming to the thermal resistances, this is what we are going to discuss it today. Thermal resistances and there are electrical resistances also. Now in this equation, the Q, which is equal to K into bracket T1 minus T2 upon the L. If we will take the T1 and T2, that is the temperature difference is there. and rest of the things are constant, that is length for a particular wall is fixed, the thermal conductivity for a particular wall that is also fixed, and the area for that particular wall is also fixed. The temperature gradient upon the resistance, the temperature difference is the driving force, and rest of the things they are considered to be as the resistances. So R resistance because of the wall, which is equal to L upon Ka. That means the temperature difference upon the resistance. That will be nothing but the Q. So we can write the delta T, which is equal to Q into the R thermal resistances or R wall resistance. In general term, R, that is the thermal resistance. So it is nothing but the temperature drop, which is equal to temperature drop or temperature difference, which is equal to the heat flow rate into the resistance, thermal resistance. This is the general term. Now, if you will look at this figure, the temperature T1 and T2 that is mentioned, the heat flow Q, which is equal to T1 minus T2 upon the R. R is nothing but the resistance that is shown in this figure. So this is the heat resistance R. Now coming to the electrical resistances. So according to the Ohm's law, the flow of electricity, which is defined as V is equal to IR. Voltage is equal to current into resistance. This is what we have already studied in the lower standards. That is the Ohm's law, which is related to the flow of electricity. A voltage is equal to current into resistance. So in this case, why the current flows? That is because of voltage difference. Why the heat flows? Because of the temperature difference. So here in electrical terminologies, the voltage is the driving force. The changes or differences in the voltage, that is your driving force. So voltage V1 minus V2 upon the resistance will be is equal to the current. So current that will be the voltage drop into the current flow into the resistance. Voltage drop, which is equal to the current flow into the resistance. That can be equated or having the analogy between the thermal and the electrical resistances concept. So this is the I, which is equal to V1 minus V2 upon RE, electrical resistance. Similarly, in case of our heat conduction, that is the heat flow rate, which is equal to the temperature difference upon the resistance. That is wall resistance, or you can say the thermal resistance or thermal resistance. So the conduction resistance of the wall, that is the thermal resistance of the wall against the heat conduction, and thermal resistance of the medium depends upon the geometry and the thermal properties of the medium. That is the thermal properties of the medium and the geometry of the medium. That is why A and L, that is incorporating related to the geometry. And the thermal properties, that is the K is the thermal property. So this thermal resistance of medium, that depends on the geometry and the thermal properties of the medium. So this can be correlated, that is your electrical resistance and the thermal resistance. So the rate of heat flow, heat transfer is corresponding to the electric current Q, and the I, they can be corresponding. Then thermal resistance, that is the R thermal and the E thermal, R E thermal and R thermal. There the thermal resistance corresponds to the electrical resistance. And similarly, what is the driving force? That is the temperature difference in case of heat transfer and the voltage difference in case of the electrical resistances. So this is the thermal resistance concept corresponding to your electrical resistances. That's the analogy between the thermal and electrical resistance concepts. Now, in addition to the conduction, this is what the conduction resistances we have considered from the Fourier law. that is K8 T1 minus T2 upon L, which is our conduction equation. Now coming to the convection equation, that is Newton's law of cooling, that gives you the convection equation, which is equal to HA into the temperature difference, that is Ts minus T infinity, where Ts is your solid temperature and T infinity is the infinite temperature, or you can say the surrounding temperature. However, this is nothing but a wall that is there, and besides that wall there is the air which is available. Ts is the wall temperature, Ts is the wall temperature, and its surrounding uniform temperature is the T infinity. My body is hot, so you can consider it as a 37 degrees Celsius body temperature, and its surrounding temperature may be say 20 degrees Celsius or 22 degrees Celsius. That can be the actual temperature, whatever. So whatever the temperature just around this surface is higher temperature as compared to the surrounding temperature. So this T infinity is my surrounding temperature, which is 22 degrees, and my body temperature, which is 37 degrees Celsius. There is a temperature drop which will take place from 37 degrees Celsius to 22 degrees Celsius. So this is Ts is 37 and T infinity is 22 degrees Celsius. So again there is a H, that is the convective heat transfer coefficient that takes place. That is, this is because of the liquids or the fluid which is available. So in that cases, Q for the convection, that can be written as temperature difference between the wall temperature and the infinite temperature upon the R resistance. So HA, that is the heat transfer coefficient, convective heat transfer coefficient H, and AS is the surface area through which the heat is transferring. So H is the convective heat transfer coefficient. So 1 upon HAS is the R convection. So it is the convective resistance. The previous one is the conductive resistance. That is, the R wall or R thermal is the conductive resistance, and R convection, which is equal to 1 upon AS. R conduction is L upon Ka. R conduction is L upon Ka. R convection is 1 upon Ha. So convection resistance of the surface, that is nothing but the thermal resistance of the surface against the heat convection. So again, in electrical analogy, you can also write the temperature difference Ts minus T infinity, which is the Q heat that is flowing through it. The resistance will be is equal to 1 upon HAS. So this is the convection resistance at the surface. When the convection heat transfer coefficient is very large, H tending to infinity, the convection heat transfer coefficient H is very large, the convection resistance becomes 0. Why? That is 1 upon infinity, that will become 0. So that is, the surface offers no resistance to convection, and thus it does not slow down the heat transfer processes. So Ts minus T infinity they will be. So this situation is approached in practice at the surfaces where the boiling and condensation occurs. So when you talk related to the convection, there the boiling and condensation processes are more concerned. Now coming to the radiation terms. Radiation equation, heat transfer rate because of the radiation, epsilon sigma into the AS into the temperature, fourth power of the temperature differences, which you can write H radiation into the AS into Ts minus T surrounding, which is equal to the Ts minus T surrounding upon the R radiation. So R radiation, which is equal to 1 upon HA radiation into the AS. So H radiation, that can be written or simplified in terms of the heat transfer equation, that is Q radiation heat transfer rate upon AS into bracket TS minus T surrounding, which is equal to the sigma epsilon and Ts square plus T surrounding square into bracket Ts plus T surrounding. So this is the related to the convective radiation heat transfer. Now the addition of the resistances, thermal resistance network, the rate of heat convection into the ball is equal to the rate of heat conduction through the ball is equal to the rate of heat convection from the ball. Here you can see the four different temperatures, that is T infinity 1, T1, T2 and T infinity 2. There is a slight temperature difference between T infinity and T1 and similarly T2 and T infinity 2. Now the first temperature difference T infinity 1 to T1, that is the rate of heat convection into the wall. So T infinity is one temperature. Let us see that this is the wall. On one side the temperature T infinity is there. This is a huge wall, you can say, so that there can be the two rooms that can be. One is the surrounding and one part is inside the room, means inside the building. ये बिल्डिंग की आउटर सरफेस है, सराउंडिंग टेम्परेचर 10 डिग्रीज है और रूम के अंदर का टेम्परेचर से 20 डिग्री सेल्सियस है और 30 डिग्री सेल्सियस है. दैट डिफरेंस इज देयर. सराउंडिंग टेम्परेचर रात का 10 डिग्री है. So that what resistance this wall offers? First resistance is the convective resistance, the rate of heat convection into the wall. This is the surrounding and this is the inside part of the room. So surrounding temperature is the lower temperature in the night cases, that is the rate of heat convection into the wall. So नाइट में टेम्परेचर रूम में का ज्यादा होगा एंड वॉल टेम्परेचर एंड सराउंडिंग टेम्परेचर वो 10 डिग्री रहेगा. सो रेट ऑफ हीट कन्वेक्शन इनटू द वॉल दैट विल बी from say 20 degrees Celsius to the T1, that is the wall temperature, and then T2 that will be there, and T infinity 2 that is the 10 degrees Celsius. So there is a one resistance, air resistance, and this is called the air film resistance, air films or the fluid resistance, the liquid film which will be surrounding this surface that will offer the resistance. This is the convective resistance, liquid film or the fluid film which is just adhering to the wall surface that will offer the resistance for the heat flow, and this resistance is the heat because of the convection into the wall. So into the wall, through the wall and out from the wall. So three resistance that is shown in this figure. So the temperature difference T infinity 1 and the T1, that is T infinity 1 and T1, which is equal to 1 upon H1A, which is nothing but equal to T1 minus T2 upon L into Ka. This is the rate of heat conduction through the wall, which is equal to T2 minus T infinity 2 upon the 1 upon H2A. So the same R convective 1, R resistance because of the wall, that is the conduction, and the R convection 2. So Q total heat transfer, that will incorporate the T infinity 1 and the T infinity 2 temperature difference, total temperature difference that has been accounted, that is T infinity 1 minus T infinity 2. That is what the total temperature difference that is accounted. And this will incorporate all the three resistances. The resistance because of the convection into the wall, resistance because of the conduction through the wall, and resistance because of the heat convection from the wall. एक है into the wall and एक है from the wall. So all the three resistances, it can be added. Therefore T infinity, then Q that is transferring, they will be same. The amount of the heat transfer through all resistances, that will be the same. So T infinity 1 to the T1. Then from T1 to T2, that is wall resistances, and R convective, that is the from T2 to T infinity 2. So total resistances, which is equal to R convective plus R wall plus R convection 2. That is 1 upon H1A plus L upon Ka plus 1 upon H2A. So all these resistances, they have accounted in terms of a overall heat transfer coefficient. This is the overall resistance. R total is the overall resistance, and 1 upon resistance is nothing but the 1 upon total resistance, which is equal to UA. U is the overall heat transfer coefficient, Q which is equal to UA delta T. एक चार पांची इक्वेशन है Q which is equal to UA delta T, which is Q which is equal to HA delta T, Q which is equal to minus Ka dt upon dx, and Q which is equal to the epsilon sigma A into T raised to 4 minus T raised to 4 surrounding. Conduction, convection, radiation, and overall heat transfer coefficient, and the heat capacity in terms of heat capacity. So these 4-5 equations we have to remember for this subject. So it is the overall heat transfer resistance, which will be incorporating from temperature T infinity 1 to T infinity 2. Once the Q is evaluated, the surface temperature T1 can be determined from the individual T infinity 1 minus T1 upon the R convection 1, which is equal to T infinity 1 minus T1 upon 1 upon H1A. So the Q that can be calculated and the individual temperatures that can be calculated. Now instead of one wall, we are putting the two walls in this figure. Two wall, wall 1, wall 2 with a thermal conductivity K1 and K2 with the wall thicknesses L1 and L2. H1 is the convective heat transfer into the wall, H2 is the convective heat transfer from the wall, into the wall and from the wall. That is in this direction, from T infinity 1 to T1 into the wall, and from T3 to T infinity 2, that is away from the wall. So all these resistances that can be accounted, and the overall resistances, so R total, which is equal to R convective 1 plus R wall 1 plus R wall 2 plus R convection 2, and that will give the total T infinity 1 and T infinity 2. That is the total temperature difference has to be accounted when we account the total resistances. And the individual, when we calculate, we will calculate Q which is equal to T infinity 1 minus T1 upon 1 upon H1A. This is for the individual temperature difference and individual resistance. This is for the overall temperature difference and the overall resistances. When we talk overall resistances, we are having the overall heat transfer coefficient, which incorporates this overall heat transfer coefficient, incorporates the resistances because of conduction, convection. Now, the instead of parallel plates, they can be in series and parallel combination. Now, here the plate A is there or wall A is there. However, the same length of B and C walls that will be there as your A wall, and there is a D wall also. So, area for B wall plus area of C wall will be is equal to area for the A wall and area for the D wall. So area through which the heat transfer that is taking place in the x direction, that will be the same. So this can be written for the overall resistances La upon Ka. In this case only thermal conductive resistances that has been accounted. You can also add the convective resistances before T1. T1 के पहले फिर T infinity 1 ऐड करना पड़ेगा आपको टेम्परेचर. So when you add T1 temperature, that is the LA into A, and for the wall B, that is LB upon A, for wall C, LC upon A. And similarly for the wall D, that is LD upon KD, as this is all wall resistances, conductive resistances. So thermal contact resistances at the contact, the temperature distribution and the heat flow line along the two solid plates. So at the plate 1 and plate 2, the no temperature drop at the interface that has been accounted. So T1 and T2 at this, they are considered to be the same. How when if they are perfectly aligned, there is no gap between the two layers. But if the certain gap is available in between the as shown in this figure, second figure, you can have a slight temperature difference, that is T1 and T2, they will not be the same. So little temperature difference that exists if the two surfaces they are not fixed. Now in this figure, you can in this pair of hand there is not a perfect matching, so there can be the temperature gradient. However, now there will not be or can be the negligible temperature gradient when the two faces are perfectly matching each other. If the two faces are not perfectly matching each other, then there can be the temperature gradient. So similarly, the other type of the resistances in parallel and series that can also be seen from this figure. Then the heat conduction in cylinders and sphere. That is the heat transfer through the pipe can be modeled as again the steady state and one dimensional, because this is the primary state we are going to consider, the steady state and one dimensional without heat generation. No heat generation. That's why we are dealing initially with the simplest equation, that is delta square T upon delta x square, which is equals to the 0. So in case of cylinder, we are having the uh, Q, which is equal to minus K dt upon dr. So area, which is equal to 2 pi r into the L, that is the surface area, outer surface area. And after integration, you will get 2 pi K L into T1 minus T2 upon ln of R2 upon R1. So temperature difference or remaining terms that will be taken into the account, the resistance. So our cylinder will have the different value ln of R2 upon R1 upon 2 pi KL. This is the resistance in the cylinder. So in the outer ln of outer radius to the inner radius upon 2 pi length into the thermal conductivity, that is the resistance in the cylinder, one cylinder. You can also add the resistance in the number of cylinders. Now this is related to the sphere. So the sphere formula, that is R2 minus R1 upon 4 pi R1 R2 into the K. So this is the R sphere. This is also, we have derived it in the previous classes. So now adding the R convection in the first, that is the T infinity 1, T1, then T2 and T infinity 2. All these four temperatures that is accounted, that is the T infinity 1 is the bulk temperature of the inside fluid, T infinity 2 is the bulk temperature of the outside fluid. That is from T2 to T infinity 2, you will get the R convection. So here 1 upon 2 pi R1 L into the H1 plus ln of R2 upon R1 2 pi KL. This is because of the cylinder, and this is because of the convective heat transfer H into the A. H A is your surface area through which the heat transfer that is taking place. So R total will be is equal to R convective plus R through cylinder plus R through outer convection. Now it can be added in series. So there are the three layers of cylinders that is there. Inside surface there is the convection, outside surface there is the another convection, convection 2, and resistance because of the cylinder 1, resistance because of the cylinder 2, resistance because of the cylinder 3. So all these three resistances that is to be taken into account.